What are radiations? A layman would know alpha, beta and gamma radiations, and this is an illustration of the relative abilities of these three types of ionizing radiations to penetrate solid matter, gamma rays being the most penetrating. How do radiations affect your life? Are they harmful? Radiation at high doses can be lethal. Radiation can cause cancer and can be harmful to the fetus at various stages of pregnancy. Can radiations be used to save our lives? Radiation therapy, also called radiotherapy, is a cancer treatment that uses high doses of radiation to kill cancer cells and shrink tumors. At low doses, radiation is used in X-rays to see inside your body, as with X-rays of your teeth or broken bones. In order to feel their presence, you need to detect them. Paranormal. How? Use radiation detectors. So there can be many types of radiation detectors. We started with the gas-filled radiation detectors, an example of which is an ionization chamber. We had already discussed in detail regarding the basic design and the current that we obtain from an ionization chamber. You got the current, and the next step will be to measure this current. So in today's video, let us talk about the measurement of ionization current. So you all know that the magnitude of ionization current that you obtain from an ionization chamber is too low, and it is really very difficult to amplify such a small current pulse. So what do we do instead? We search for something that is related to current, and this something is comparatively easier to amplify. What is that? Voltage. V is equal to IR. If you use a value of resistance which is sufficiently large so that the product of current and resistance leads to a value of voltage whose order is much better as compared to the low value of current, in that case you can measure your voltage, and its subsequent amplification is comparatively much easier as compared to the amplification of the small current. Well, is there anything so far that has been invented to serve this purpose? We have electrometers. So electrometers are highly sensitive devices or instruments which are used to measure small electric charge or voltage. So in this picture you have an ionization chamber and an electrometer, and this is how they look together. So their basic function is to detect the presence of charge, to measure the amount of this charge and the potential difference between 2 points. The device typically consists of an input terminal for the charge to be measured, a sensitive electrometer amplifier, and an output for displaying the results. The heart of an electrometer is the electrometer amplifier, which is responsible for converting the input charge or voltage to a measurable output signal. It's always a good idea to talk a little bit about the history. Go back to your school days. I clearly remember that there was something called a gold leaf electroscope. So what was that? It consisted of a thin brass rod with a brass disc at the top, and at the bottom you had two thin gold leaves. So what happens is that if you bring a charged rod, if you bring a positively charged rod near this brass disc, what happens is that charging by induction takes place. The positive charges will be repelled, and this will enable this disc to acquire a net negative charge. Since the brass disc and brass rod is interconnected, it will result in the leaves to acquire a net positive charge. As a result, these two leaves, they acquire positive charge, and like charges they repel each other, so the leaves will diverge. So the gold leaves will diverge. Similarly, you can charge the rod by conduction as well. So what is the primary use of this gold leaf electroscope? The first function is that you can identify whether a body is charged or not. So how can you do this? Touch that object to the brass disc. Now, if the leaves do not show any movement at all, what does that mean? That the object was uncharged. And if any movement is seen with respect to the two leaves, that means that you have brought a charged body near the surface. So this can detect the presence of charge. Another thing that it can do is that it can also tell us about the polarity, whether the charged body is positively or negatively charged. So in this case, you need to first charge your electroscope. Once you have done this, you will know that your leaves are positively or negatively charged. In either case, since the leaves will acquire like charges, they will repel. So the next step will be to bring that charged object near the brass disc. Now if the leaves further diverge, If the leaves further diverge, that means that the object was positively charged, and if they come closer, if they cling together, that means that the object is negatively charged. This was all about the basic history of the gold leaf electroscope. So we can say that initially electrometers were simple devices that used the principle of electrostatic repulsion to measure the presence of charge. So over the years, the sensitivity and precision of these electrometers have drastically improved. We now have quartz fiber electrometers and solid state electrometers. So let us now talk about the basic principle of electrometers. The basic principle of operation for an electrometer is the use of electrostatic force or capacitance to detect the presence of small charges or voltage. Now this electrostatic force, this has already been discussed for the case of gold leaf electroscope, wherein this principle was used to detect the charges. Now coming to the capacitance, you know capacitance can either be fixed or variable or dynamic. And for the case of fixed capacitance, we have DC electrometers, and for the case of variable capacitance, we have AC electrometers. Capacitance, as you all know, is written by this formula epsilon A by D, where this is the permittivity of the free space and it is constant, having SI units farads per meter. Farad is the SI unit of capacitance. A is the area of overlap of the plates, the two plates of the capacitor, and D is the distance between them. So this is the general formula, as you all know, for the capacitance. Coming to the case of fixed capacitance, I told you that we use DC electrometers in this case. So this construction looks familiar to all those who have gone through my previous video on design of ionization chamber, wherein we have discussed in detail regarding the guard rings, why do we use them, the high value resistors that are used in ionization chamber. If you have any doubts regarding this, link is there in the description box. You can go through that video, and you should go through that video before coming to this video. Everything else is exactly the same except for this capacitor and this resistor. You had an ammeter over here. Construction of an ionization chamber, you had an ammeter. So instead of that, now I have drawn a fixed capacitor here, capacitor with fixed capacitance, and then you have a resistor. So what you will be getting? You will be getting a current pulse. A current pulse will be the output of the detector, which will be converted to a voltage pulse. So the pulse that you will be getting through this resistor R is VR, and that is voltage pulse, and it is this very pulse that will be measured by the DC electrometer. You had current. You know that the order of current that you get from an ionization chamber is of this 10 to the power minus 12 ampere. So instead of measuring current, it was always a good idea to measure something else which is related to current. And what is that? You have voltage. This is Ohm's law. V is equal to IR. Now the order of current is this, and you know that the resistance value that you use for the ionization chamber is of this order. So if I take these two values, the voltage that you will be getting is 10 to the power minus 12 amperes into 10 to the power 12 ohms, which comes out to be 1 volt. It is clearly visible from here that it is much easier to amplify this voltage signal than to amplify this current signal. The basic principle of DC electrometers was this. Now the major drawback. So you know that everything comes with its advantages and disadvantages. Talking about the major disadvantage for the case of DC amplifier, it is the constant drift. The constant drift that is observed for this case. What is drift? Drift is any unwanted change in the output voltage without any change in the input voltage. And this drift is primarily caused by changes in temperature, and you know that amplifiers being semiconductor devices, these are susceptible to temperature changes, and any variations in the amplifier output because of the variations in temperature will lead to a drift, and it is always a good idea to minimize this drift by controlling the temperature changes. So DC electrometer will be using an inbuilt DC amplifier. Why? Because you have a DC output voltage. and not AC. Now this major drawback of drift observed for the case of DC amplifiers within these DC electrometers is rectified or eliminated to a major extent by the use of AC electrometers. In this case, you will be having a variable capacitor. So variable capacitor, everything else is same except for this. So you have a variable capacitor over here and a resistor. And if you use a variable capacitor, you can convert your DC voltage into AC voltage. So if this change is brought about at an early stage, that is the conversion of DC to AC by the use of this variable capacitor, this work of processing the amplification in the subsequent stages, this work can be drastically reduced. Talking about how this conversion is brought about. How can we do this? You know that the formula for static capacitance is this. Now for a constant charge, you have the voltage, charge and capacitance are related by this formula. Now for the constant value of charge, you will see that voltage is inversely proportional to the capacitance. If this is constant, I can say that V is inversely proportional to C and C in turn is given by this. So if in case I am saying that C is variable, if C is variable, the only way to make it variable is only if you are able to change the distance between the plates of the capacitor. How? Because this epsilon, this is a constant, it is having this value and A is the area of overlap. You cannot be changing this continuously once you have fixed your capacitor plates. Now the only thing that you can do is to vary the distance between the two plates. So a change in capacitance is brought about by the change in the distance between the two plates. So if this voltage V is made variable with respect to this capacitance, so dV by dC will be this minus Q by C square. Simple differentiation we have done with respect to C, and Q is equal to CV. So putting the value of Q over here, you will be getting this relation. So this is given by either this or this. And if you take this DC over here, so the output voltage that you will be obtaining is related by this. Now from this relation, I can say that if somehow this capacitance, this change in capacitance is sinusoidal. This change in capacitance is sinusoidal, that is, it is a type of AC variation. That is, it is varying periodically. I can easily say that my output voltage is AC now. So what has to be done for this case is, if your capacitance is given by this formula, if it is given by this formula, C naught sin omega t, where C naught is the quiescent value, the value of capacitance when this setup is in the dormant state, when it is not moving. So this change in the value of capacitance will give you this expression. Simply we have differentiated this expression. Now this angular frequency is related to frequency via this relation. So instead of omega, I can write this 2 pi f. Now this value of DC comprises of this cos omega t term and this frequency. So if I put this value over here, I can clearly say that my output voltage is now varying periodically with time and uniformly. So it is a sinusoidal type of variation. So if somehow I'm able to do this, then I can obtain my AC voltage from DC voltage. And how can we do this? A simplified example of this is represented over here. So if you have a DC input here, this is a capacitor. Now this capacitor will comprise of two electrodes. One is fixed, and to this fixed electrode you will be applying your DC voltage or current that you need to convert into AC. And this movable electrode is the other plate of the capacitor which is moving with respect to this fixed electrode. So these are the two plates of the capacitor, and now this change is brought about. This change in distance of the two capacitor plates is brought about by the use of these transducers and variable frequency AC generator. So what happens is that variable frequency AC generator will generate an AC signal of frequency which is equal to, generally taken as equal to, the resonant frequency of the transducer. The frequency where the ceramic element in this transducer vibrates with its maximum or highest amplitude is the resonant frequency of the transducer. So this is chosen to be equal to this. So if this new frequency of this AC generator makes the ceramic element in this transducer to vibrate in its flexural mode. Now a specimen may vibrate in any of the modes that are flexural, torsional, longitudinal or planar. Now the work of transducer is to convert one form of energy to the other, and for the case of ceramic transducer, we are converting the electrical energy into mechanical energy. This force of bending enables these plates or beams to vibrate in flexural mode. So it will be like this, uniformly and constantly moving with the same frequency as the frequency of the variable AC generator. So this drives this transducer, and the ceramic element in this transducer is now vibrating. This transducer is in turn connected with the movable electrode. And what happens is that all three of them, they vibrate in unison, in unity together. So the same frequency from here to here to here. This means that the frequency with which this movable electrode is vibrating is the same as the frequency of the AC generator, which is given by nu. Now as this movable electrode is moving with respect to this fixed electrode, and these are nothing but the plates of capacitor, you can say that this distance, it begins to vary. It's a constant and uniform movement with respect to this fixed electrode, and you can say that this is moving, so this is changing. So if C is changing, your V is changing. And how is this variation? This variation in C is sinusoidal. Why sinusoidal? Because the frequency from here that you are giving is AC. So this frequency F is nothing but the frequency nu of this AC generator. So the conversion efficiency of a vibrating capacitor is given by this, which depends upon the RMS value of the output AC voltage divided by the DC input value of the voltage. And from here also you can see that this voltage will consist of this frequency of the variable frequency AC generator. So the conversion efficiency from DC to AC is dependent upon the frequency of the variable frequency AC generator. So it is to be noted that not only the change of this fixed electrode with respect to the movable electrode be constant and uniform, but it has to be brought about at a very quick rate. The frequency of vibration of this movable electrode with respect to the fixed electrode should be large enough. So in the case of AC amplifiers, the problem of drift is drastically reduced. That was earlier seen with the DC amplifiers. So this was all about how we can obtain AC from DC. And another important thing that you will note over here is that this C comprises of the chamber plus any parallel stray capacitance. Now you understand the chamber capacitance, that will be the capacitance of this ionization chamber. But what about this stray capacitance? The parallel stray capacitance. This is something new. This is an interesting topic which will be discussed in my next video. Thanks for your patience.